Today we're going to cover section 1.4 in our book about dual spaces. To start, we need to define what a linear functional is, as they will become the most important part of what we're discussing today. A linear functional is a very special type of linear transformation that has a very specific domain and range. To define it, we have the following. A linear functional on a vector space U, where U has the field of scalars F, is a linear map from that vector space U to its field of scalars F. So the domain has to be the vector space U, and the codomain is the field of scalars F. Because it's linear, this means that the function will preserve both vector addition and scalar multiplication. That's what these two properties are here. Moreover, if you have any two linear functionals, f and g, then how they behave and interact together follows just general definitions of how functions behave. So for example, you can add two functions and that's defined normally. Or you can multiply that scalar by that function and it just multiplies all the values of that function by that scalar. These two properties here define a vector addition and a scalar multiplication on the set of linear functionals, and you can check that that definition actually preserves and satisfies all the axioms of a vector space, which shows that the set of linear functionals on U forms a vector space itself. So what is the dual space? The dual space is simply the vector space of linear functionals on U. So the dual space U prime, that's how we denote it. Some books will use a U star, but our book uses U prime, so that's what I'll use throughout the lecture. The dual space U prime of a vector space U is the vector space of linear functionals on U. All right, so the collection of all those linear functionals on the last slide that act on a vector U and produce a scalar, the collection of all those functions are what we call the dual space. Because it's a vector space, it also has a basis, but there's actually a natural corresponding basis between any basis for U and a basis for U prime, and this is the notion of a dual basis. So if I start with a basis for U, say B here, the set of linear functionals B prime that's defined as follows will be what we call the dual basis. Now note, because the linear functionals U1 prime to UN prime are linear transformations, I only have to show how they're defined on a basis, and then you extend it linearly, and that tells you how that functional is defined on the entire vector space. So we'll use the basis B to define the functions U1 prime to UN prime. And how it'll work is Ui prime will act on Uj to produce what's called the Kronecker delta. I'll describe what this is in just a second. Another notation for this same thing, plugging Uj into Ui prime, is sometimes written this way. Okay? This Kronecker delta is a fancy way of writing down the identity matrix, because what it is delta ij will equal 1 when I is equal to j, but it's equal to 0 when I is not equal to j. That's what we call the Kronecker delta. Kronecker is a guy's name. So this set here, B prime, of U1 prime to UN prime, is the dual basis to U1 to UN. And the way it acts on that basis B is via the Kronecker delta. We'll prove a little later that the dual basis actually is a basis, so that you can see that, but for now we'll have to trust it. On this slide, we want to look at a few other definitions and theorems that come up with regard to dual spaces. The only other definition I really want to point out is that of the annihilator of a set. So if I take a set S that's a subset of a vector space, notice S does not have to be a subspace, just a subset. Then the annihilator of that set is the collection of linear functionals that annihilate every single element in that set. And by annihilation, what I mean is that if I take any element u in the set S, then all the linear functionals that send all of those elements of S to 0 are the linear functionals that are in the annihilator set. We'll use this a little bit later in a few future sections, so I wanted to make sure we had the definition down here. It won't play too much of a role in the rest of the video today. Some important theorems to know about the dual space, some of which we can prove real quickly. Others we'll prove a little bit later in this lecture, are the following. The first is what we proved earlier, that the dual space u prime of u is in fact a vector space on its own. That's an important takeaway. That u prime has the same dimension as u. And we know this because the dual basis, which we showed on the last slide, which we will prove on the next slide is actually a basis, has the same number of elements as the basis for u did. That since the dimension of a space is defined by as the number of elements in a basis, this shows that the dual space and the space itself have the same dimension. Next, if we take the double dual, or the dual space of the dual space of u, so u prime prime, there's actually a natural isomorphism between u double prime and u. Now, of course, they're all vector spaces of the same dimension. So technically u prime, and u double prime are all isomorphic because they're vector spaces of the same dimension. But the relationship between u double prime and u is actually more natural than just simply having an isomorphism between them. So we'll explore that a little bit later in the lecture as well. Finally, you can actually write down how the change of basis matrix between two dual bases behaves with regard to the change of basis matrix to their original bases. So if you start with two bases of u, b and c, and they have a change of basis matrix A, and b prime and c prime are their corresponding dual bases of u prime, then the following is true. You can see that A is taking b coordinates into c coordinates, and A transpose will take c prime coordinates in the dual space to b prime coordinates in the original space. There should be a prime right here. I think that's a little bit of a typo. That should be b prime. Okay, and we'll prove this in a minute, show how this works. That's all the major content from this section that we wanted to get out of it. The rest of this lecture will be proving some of the statements that we said here, and then we'll also do an example exercise. But you could stop here if you wanted to take a break and try to absorb some of this content. Those are all the main ideas from this section. All right. The first thing that we'll prove is that the dual basis is in fact a basis of u prime. To prove that a set is a basis, we have to show both linear independence and that the set spans the space u prime. So remember, when we're talking about the dual basis, we're talking about those elements u1 prime to un prime that are dual to the basis elements u1 to un. The way that u1 prime to un prime behaves on u1 to un is via the Kronecker delta. If you want to review that real quick, you can pause the video and jump back a few slides to see how we define that. All right, to show linear independence of these vectors, we need to consider an arbitrary linear combination of the vectors u1 prime to un prime and set it equal to 0, and solve for the coefficients a1 through an. If we can prove that the coefficients a1 through an have to be equal to 0, then the set of vectors u1 prime to un prime must be linearly independent. Note that the left-hand side of that equation there is in fact a functional in its own right and happens to be equal to 0 no matter what vector u we plug into it. We'll use this to our advantage and plug in every one of the basis vectors u1 through un. We'll do this with an arbitrary one, uj. So we know that this is going to equal 0 when we plug it in, no matter what. So when we plug in uj, and it's going to be 0 no matter what the index j is, it ends up plugging into each of the individual pieces, u1 prime to un prime, by definition of how functional addition and scalar multiplication behaves. Now, the ui primes will cancel the uj's and give it 0 except when I equals j. So the only thing that survives here is when we have uj prime acting on uj. And in that case, it produces a 1. So the only thing we get out will be the coefficient aj. But this means that aj is in fact equal to 0. But j was arbitrary. So if you just run through all the j's, you can show that a1 through an all have to be 0 in order for this to work. So the only solution for the linear combination equals 0 above there, this equation here, the only solution to this equation here is the trivial one, that a1 through an are all 0. This implies that the set B prime, which is equal to u1 prime to un prime, is a linearly independent set. Now let's talk about the fact, let's try to prove the fact that it's a spanning set. So to do this, we'll start with an arbitrary element f in the dual space. If we can show that f can be written as a linear combination of the u1 to un's, then we've shown that the u1 to un spans all of u prime. This is because f is an arbitrary element of u prime. Now remember, f is a linear functional. In particular, it is a linear function, and hence is completely defined by how it acts on a basis. So to start off with, let's identify the values that f takes on the basis u1 through un of u. We'll let bj be the value of the functional f on the uj elements from the basis of u. So f of uj equals bj. Now, use those elements b1 through bn that we just defined to define a linear combination of the u1 primes to un primes. And we'll call this linear combination G. What we plan to show here is that the linear functional G is in fact the linear functional f. To do this, all we have to do is show that G and f, because they're both functions, we just have to show that they agree on every element in the vector space. But since they're both linear functions, we actually only have to show that they agree on a basis. Since we already know how f behaves on a basis, all we really need to show is that G behaves the same way on that basis. That is, we need to prove that G of uj for any j, whatever j we pick, will in fact be equal to bj. So let's plug uj into G, and we get the following. Again, because of the way function addition and scalar multiplication behave, this is plugging uj into each of the ui primes to un primes in that linear combination. And just like this equation over here, the only thing that survives is the j coefficient. So G of uj does in fact equal bj. And this shows that f and g agree on a basis, which means that they have to be equal as functions. That means that we have now written f as a linear function, a linear combination of the u1 primes to un primes. Since f was an arbitrary element of u prime, this shows that b prime is in fact a spanning set of u prime. Putting the fact that it's a spanning set and linearly independent together, this proves that b prime is in fact a basis of u prime. The next thing we want to prove is that u double prime is naturally isomorphic to u. Now, it is true that it's isomorphic to u simply by virtue of the fact that they have the same dimension. And you can show that really easily as follows. Let's let b prime, and b double prime be a basis for u. So b is the basis for u, b prime is the corresponding dual basis of u prime, and b double prime is the dual basis of b prime in u double prime. Okay? Then all we have to do is define the correspondence of uj. So let's say B is the vectors u1 through un, and we just add a prime for each of the dual bases. So we'll define the correspondence uj to uj double prime and extend that correspondence linearly. This is clearly a linear transformation because we extended it linearly. It's clearly bijective because it's a correspondence between the basis vectors, and hence it's a vector space isomorphism. This is actually why any two vector spaces of the same dimension happen to be isomorphic, because you can just simply line up their basis vectors, and that creates a linear vector space isomorphism between the two. So that's not the interesting part. The interesting part is actually how we can relate uj double prime to uj. The correspondence becomes more natural when we recall how the dual bases behave on each other. So if you remember back from the dual basis page, if you go back a few slides, you'll remember that we got this equation here. That the way uj prime or ui prime behaves on uj is via the Kronecker delta. But we had this really cool bracket notation for it, okay, which is kind of helpful here. Well, the uj double prime vectors in B double prime behave on ui prime kind of the same way. You get the same relationship, it's just that now the double primes are the dual basis, okay? And you get this little angle bracket here, which gives a delta ji, but delta ji is the same as delta ij, because remember the Kronecker delta really just basically represents the identity matrix, okay? What this shows is that the uj's, if you think of the uj as being the actor here, it acts on the ui prime the same exact way the uj double prime does. They both hand back delta ij. Because of that, you can kind of think of the uj as the function and the ui prime as the input, and if you do that, the new function you find from this equation here, the new function you find is precisely uj double prime. And this gives a sort of natural way of lining up uj and the uj double primes. And so when we say that u double prime is naturally isomorphic to u, we mean it in this sense, that essentially u behaves exactly like u double prime does, even when it's interacting with u prime itself. So that's what we mean by saying that the dual of the dual is the original space. So u double prime, we can identify it with u in a very, very natural way. And pretty much from now on, we will make this identification and even sort of misrepresent it a little bit by abusing the notation, and we may even say that u double prime actually equals u, when technically they're different as sets. But if we view u from a certain point of view, it behaves exactly the same way. And so there's no reason to really make the distinction. All right, the last main idea that we want to prove, and then we'll get to an exercise, is to prove that the dual change of basis matrix is in fact just A transpose. So this takes a little bit to set up. First, let's let B, which is U1 to UN, be a basis, and C, which is V1 to Vn, be another basis for U. Let's say that the change of basis matrix for them is A. This will convert coordinates in C to coordinates in B. To put this another way, to remember this gets a little complicated from our lecture on Monday, but what it means essentially is that the columns of A are the coordinate vector representations of the C vectors with respect to the B vectors. Okay, so the columns of A are the coordinate vectors of the basis vectors in C with respect to the B basis. B prime will be the dual basis to B, and C prime will be the dual basis to C with the usual notation. Their change of basis matrix will be A prime, but then in this case, it'll change the basis the other way. So A prime will denote the change of basis matrix that converts coordinates in B prime to coordinates in C prime. So the columns of A prime are the coordinate vectors of the B prime vectors in the C prime coordinates. To write this mathematically are the following two equations. So you can see here that the Vj coordinates are written as the columns of A are their coordinate representations on the UI. So the columns of A represent the linear combination coefficients on the UIs that produce the VJs. And the UJ primes and the VJ primes have the same relationship here, just sort of swapped with the AIJ prime. Once we have that, we can do a computation two different ways. What we're going to do is we're going to compute UI prime on VJ, and we're going to do it two different ways. First, we're going to plug in what VJ is and let UI prime act linearly on it. Then we're going to plug in what UI prime is equal to and let that behave as a function on the VJ and see what we get. So in this first equation, we're looking at expanding the VJ according to this equation right here. So we plug in that right in here, and then UI prime acts linearly on it. So the AKJs will pop out, and the UI primes will all behave on the UKs. The sum also pops out. Well, this is just simply delta IK, which is what we get here, but we're summing over K. Well, delta IK is equal to 0 except when K equals I. So the only thing we get out is AIJ, this guy here when K equals I. Okay, because delta II will be 0. Well, sorry, will be 1, and delta IK will be 0 if K is not I. All right, now let's do the computation the other way. Let's now expand the UI prime in this equation. We get this sum here, which is a sum of functions, each acting on the VJ. So according to the definition of how function addition and scalar multiplication works, this is how it separates out. So we have the AKI primes to VK primes on the VJ. Now again, this right here is just the Kronecker delta, and it produces delta KJ. But we're summing over K. Delta KJ is equal to 0 unless K equals J, and in that case it equals 1. So the only thing that survives this sum is AJI prime. What this means is that AJI prime equals AIJ, or that all the elements in the AIJ prime matrix equal the sort of transposed element in the A matrix. So to rewrite this, this is actually the statement that A prime does in fact equal A transpose, which is what we set out to prove. So that's kind of an interesting way that the change of basis matrix behaves. It turns into a transpose and goes the other way. So you start with a matrix that goes from coordinates in C to coordinates in B, and its transpose will take B prime coordinates to C prime coordinates. Kind of a little wonky, but also shows a little more of the relationship between the vector space and its dual. We'll wrap up this lecture with a sample exercise. This is exercise 1.4.3 in the book, and it says the following. If U is a finite dimensional vector space and F and G are elements of the dual space to that vector space, so F and G are linear functionals in U prime, and they're such that they annihilate exactly the same vectors. So F of V equals 0 if and only if G of V equals 0. It doesn't matter if they share any other values, but they just have to be 0 on the same set. What we're going to prove is that in that case, F and G are linearly independent. Which, if you want, you can think of it this way. If you have two vectors that are linearly dependent, that means one of them is a scalar multiple of the other. We'll simply just show that, that there's a non-trivial linear combination of F and G that produces 0. To start, note that if F is identically 0, then the set FG has to be linearly dependent because it has a 0 vector in it. Moreover, it would in fact make G 0 as well, so it would actually have two 0 vectors in it. So in that case, it's simple to show that they're linearly dependent. So let's take the more interesting case where F is not equal to 0. This means that there's at least one value of U in the vector space U that F does not annihilate. So F of U has to be not 0 for that vector. But that also means that G has to not annihilate it. So G of U has to be non-zero. Because if G of U were 0, then by the condition in the hypothesis, F of U would have to be as well. So if one's not 0, they have to both be not 0. We'll use this guy later. We're going to let the value a be equal to the ratio of g of u to f of u. Since both of those values are non-zero, the fraction between them is non-zero. And remember that they're both field elements, so when we say fraction, we really mean division in that field. So g of u divided by f of u is really g of u times the multiplicative inverse of f of u. But we'll write it as g of u over f of u for shorthand. Now, let's let v be any element of u, so it's any vector. And define the following vector off of v and u. So w is going to be the vector v minus the fraction f of v over f of u, which is a scalar, times u. Notice we can divide by f of u because f of u is non-zero. Now let's compute f of w. Note that f of w, we can use the fact that f is linear and plug in what w means to get the following equation. So we distribute f linearly and we get this equation here. The f of u's cancel and I get f of v minus f of v, which is in fact 0. So w is annihilated by f, but by the hypothesis that means g must also annihilate it, so we have g of w has to be equal to 0 as well. Now let's take that fact and see what we can do with it. Because 0 equals g of w, if we plug w back into that equation and now have g act linearly on it, what we'll find is that when g pops through linearly, we get this here. So no longer does anything cancel, but we can swap the numerators, g of u and f of v, to get this equation here. G of u over f of u we define to be a. So this produces this equation here, which if you remember was equal to 0. So another way to write this is this tells us that g of v is in fact equal to a times f of v. But v was arbitrary. So this means that these functions agree at every single point in the vector space. And hence g minus af is actually identically equal to 0, meaning that g minus af is in fact the 0 function, and now we've shown a non-trivial linear combination because a is non-zero and g's coefficient is 1. This is a non-trivial linear combination that equals 0, which means that g and f must be linearly dependent, and proves the theorem. All right, guys, that's all I had for you for this lecture here. I'm sorry it went a little bit long. Hopefully it was clear and went slow enough that you can pause and go through what you need to. If you have any questions, feel free to send me an email. Otherwise, we'll see you in the next video.